We now continue with Milica Ðukic, who will tell us about the deformation of the Chekanov-Eliashberg DGA using annuli.
Thank you very much. It is a great pleasure. So as the title suggests, I'm going to talk about an invariant of Legendrian knots in R3, which comes from symplectic field theory framework and extends the existing invariants that are obtained by counting holomorphic disks by introducing J-holomorphic annuli into the picture. So it's an extension of Chekanov-Eliashberg algebra and rational SFT. And I'm going to take some time to introduce the setting. So the basic setting is we consider Legendrian knots in R3 with a standard contact structure, i.e. embeddings tangent to the contact hyperplane distribution kernel of the one form dz minus y dx. And convenient ways to see these knots is by using front projection, i.e. projection to the xz plane, or Lagrangian projection, i.e. xy projection. So here we have front projection and Lagrangian projection of some Legendrian right trefoil. And now Legendrian isotopy between two such knots is a path of Legendrian knots from one to the other. And the main question we want to ask is how can we distinguish two Legendrian knots up to Legendrian knot isotopy? And this question already is quite difficult in the smooth case, but we can also have distinct Legendrian knot invariants, distinct Legendrian knot classes within the same smooth class. And to distinguish those, we can use some existing invariants that are stronger than the smooth invariants in this setting. So this includes classical invariants like Thurston-Banachine number, rotation number, and SFT-type invariants like Chekanov-Eliashberg DGA and rational SFT. And I will briefly just introduce those, but I guess everyone should have heard about it. So Chekanov-Eliashberg DGA is some algebra, well, technically tensor algebra generated by the Rabe chords with grading given by some Maslov index, and the differential in a way counts index 0 pseudoholomorphic disks with one positive puncture living in the symplectization R4 with boundary on the Lagrangian cylinder R times lambda. And rational SFT is continuation of this story defined by Leonard Ng, and the differential here counts index 0 pseudoholomorphic disks with arbitrarily many positive punctures, and it also has another part, which in a way is a string topological deformation, and it inserts trivial strips. In a way, it takes a string product with trivial strips and is necessary to cancel out some sort of nodal breaking. The underlying space is the vector space generated by cyclic words in QI, PI, so 2 letters for each Rabe chord representing positive and negative punctures. So here is a figure that should represent possible SFT breaking for disks in dimension 1 moduli spaces. And here we have these SFT buildings. In addition to that, for disks with more than one positive puncture, we can have trivial strip breaking. And the string topological part should in some way cancel out those. So similar thing will appear now in this other invariant, which is the next step in this SFT story. So we define an invariant that also includes J-holomorphic annuli, and we describe a way how to compute everything combinatorially from the Lagrangian projection. So more precisely, for every Legendrian knot, we define something which I call second order DGA, which is invariant under Legendrian isotopy up to a certain kind of stable tame equivalence that is an analog of stable tame equivalence for DGAs of Chekanov. And in particular, we get a chain complex such that for Legendrian isotopic knots, the corresponding homology groups are isomorphic. Moreover, we show how count of annuli, which is part of the differential, can be replaced by certain sections, obstruction section type sections with certain properties, which give us a combinatorial way to compute the invariant from the Lagrangian knot projection. And the main story behind it is the SFT framework of Eliashberg given Talhofer. So I will now introduce the invariant. So first, the underlying space will consist of two parts. One part is the same as in the Chekanov-Eliashberg algebra, the tensor algebra generated by Qi. We will also need these homological coefficients, which will keep track of the homology class of the boundary. So we add one generator and its inverse. And the differential will consist of three parts. The disk, which counts disks, the annulus, which will count annuli, and a certain string topological part, which will resemble something like string coproduct. And some quick remarks here. Here, if we take h bar is equal to 0, we will get the standard Chekanov-Eliashberg DGA. And one useful way to see these elements in this algebra is by seeing them as strings or pairs of strings on the Lagrangian cylinder with negative punctures at the corresponding chords up to homotopy relative ends. So that will be useful later. But now to get as easy computations as possible and definitions, it's good to have as much algebraic structure as possible on our geometric objects. So the natural algebraic structure that kind of appears here is something that can be thought of as a non-commutative version of BV algebra. And it consists of a degree -1 linear map D that squares to 0 and a bracket such that certain relations are satisfied. And we don't have to look really into these in details. It's good to say that basically all of them are some type of Leibniz rule. This first one is special. Here it tells us that D is actually not the derivation with respect to this algebra product, but in addition to this Leibniz type rule, we have this bracket. So it looks like this BV algebra relation. And yes, now we can go on to define these three parts of the differential. First, the disk part. Basically, for a string W, the disk of W is obtained by gluing positive punctures of an index 0 pseudoholomorphic disk to this string in all possible ways. And more precisely, we can say it by saying that the disk of Qi is sum over all index 0 J-holomorphic disks with one positive puncture at gamma I of words obtained by reading off the negative punctures at its boundary in the order starting from the positive puncture. And we will add this t plus minus every time we cross with the boundary over r times t for t some fixed base point. And the bracket at Qi, Qj, the disk part of the bracket, will be sum over J-holomorphic disks of index 0 with two positive punctures, one at gamma I, one at gamma j, of tensor product of words where the first word is just the word consisting of negative punctures from the positive puncture at gamma I to the positive puncture at gamma j, and the second word from gamma j to gamma I. And the figure below should explain how this should look like geometrically, and the algebraic relations are just made so that everything works. And the annulus part is similar. Here we are going to consider only annuli with one positive puncture. So this bracket component of annuli is going to vanish. And dA of Qi is going to be sum over all J-holomorphic annuli of index 0 of tensor product, word tensor product cyclic word. The first word comes from negative punctures on the boundary component that contains the positive puncture. And the second word is the cyclic word of negative punctures on the second boundary component. And for the second word, there is no natural starting point, so it should really be seen as cyclic word. And finally, for the third part, string topological part, we are going to take a generic string representative on our cylinder. And an important part here is that we need to take certain asymptotic behavior of this string, which models generic asymptotic behavior and generic relative asymptotic behavior of pseudoholomorphic curves. And we take a spanning disk for this string which is holomorphic at the boundary. And then we define ds of W to be sum over all self-intersections of the string of pairs of strings obtained by resolving the self-intersection plus one summand plus minus h bar the string tensor 1 for each interior intersection of the spanning disk with the cylinder r times lambda. So the first part is basically string coproduct, and the second part is some sort of deformation that is useful in this setting. And now to define this, we used some sort of choices, but ds doesn't actually depend on any choices, and that's not very difficult to see. So it doesn't depend on the choice of representative string or the spanning disk. And here we have maybe an example to see. We can consider one-dimensional moduli space of disks as in these figures. And on one side, we have a disk that's close to breaking into an SFT building, but doesn't have any interior intersections with the cylinder, but has one boundary self-intersection. And on the other side, we have disk that's close to breaking off a trivial strip and has one interior intersection with the cylinder, but no boundary self-intersections. And in this case, ds of this string is equal to h bar string tensor 1. Okay, so there are more precise algebraic formula that one can write down here what ds is, but we don't have to go into detail. Now, maybe one can say that in ds of qi, linking number of the capping path of this negative puncture appears with the knot lambda, and the capping path is shifted off of lambda in some specific way. All right, and now we can define our differential as the sum of these three components. And the main statement here is now that d squared equals to 0. So the proof idea is the standard SFT philosophy. We consider the boundary of the one-dimensional moduli space of pseudoholomorphic disks and annuli. And I have already shown you what can happen for disks. And for annuli, we have these standard building SFT buildings. In addition to that, we have two types of nodal annuli. One type where some path between the two boundary components shrinks to a point and gives us a rigid disk with boundary self-intersection. That's in this dimension. And the second type where the boundary without the positive puncture shrinks to a point and gives us a rigid disk with interior intersection with the cylinder. And this string topological component is really designed in such a way that these two components appear in D square. And this idea was inspired by work of Fukaya, Chilibak, Flachev. One difference is that they deal with the second kind of nodal breaking in a different way. And here we managed to retain as much information as possible from these curves. And now that concludes the first part of the talk, where I defined the invariant. And now for the second part, I want to say objects, and that also gives us another way to prove, for example, invariance of our invariant. So SFT otherwise would come with some sort of transcausality issues when you try to prove invariance, but this combinatorial approach totally avoids those and works in this setting. So generally, if we take some almost complex structure J, counting these J holomorphic curves is generally difficult, but we can choose a special almost complex structure given by this formula here and take generic knot so that these moduli spaces are actually regular. And now what is special about this J almost complex structure is that projections, Lagrangian projections, are actually holomorphic curves. And it is well known that index 0J holomorphic disks on these cylinders are in bijection with immersed holomorphic polygons in the Lagrangian projection with convex corners and boundary on the projection of the knot. But now for annuli, the story is slightly different because their first homology class doesn't vanish. So here actually projections of these index 0 J holomorphic annuli that we want to count belong to one parameter families of holomorphic annuli with corners. And to see this in a way is good to, for example, look at some rigid annulus and try to lift it. So let's cut it into a disk and lift it in some certain way. Then we can see that the two branches at the cut might not match up and give us actual smooth annulus, and there will be some sort of distance between them, which we will denote by omega. So this gives us an idea that codimension 1 subset of our holomorphic annuli can be lifted up to the symplectization. And here is an example of what can be a rigid annulus on this figure 8, not projected to the Lagrangian projection. And we will actually see soon that there will actually be count plus minus 1 annulus in this family. And what I said, one can now put together into the following. So if we denote by MP, the k-dimensional moduli space of holomorphic annuli in the Lagrangian projection, then there exists a smooth section omega from this moduli space such that an annulus can be lifted to a J holomorphic annulus in the symplectization if and only if this section vanishes on it. Moreover, omega is transversed to the zero section for generic lambda and has some specific behavior at the boundary. So one can see what the limit is at the boundary of this obstruction section. And maybe I better show it on these examples. So there are two types of boundary of these holomorphic annuli in the projection. One that we'll call non-split, where the branch point hits into boundary component that it doesn't belong to. And the second, as in this third figure, where the branch point hits the boundary component where it belongs to. And in the first case, we get a disk with two additional positive punctures in the limit. And in the second case, we get a disk bubble together with an annular part, which is a rigid annulus in the projection. So the obstruction section in the first case is going to converge to plus or minus infinity. In this first figure, it will converge to plus infinity, in the second to minus infinity. And in the second case, it will converge to the value of this obstruction section at this rigid holomorphic annulus that is the annular part of the limit. So one can, for example, now already see that what I've said here, we have one parameter family of annuli here with parameterized by the image of the branch point on these two arcs. And the value of the obstruction section on one side goes to plus infinity, on the other side to minus infinity. So the count of annuli should be plus minus 1. And one can define some orientations here. It is actually necessary to work with Q coefficients, but I didn't say that, may be important. Yes, so here we can see that. And we can conclude more. We can say that, okay, now if we know the values of omega at M0P, we can actually count all index 0 annuli. However, yeah, even more, we don't even have to know the actual values, but we know if we know the signs. However, even the signs might be difficult to compute. So we have the following way, which says that we can replace these omega actual obstruction section with certain slightly more flexible sections with similar properties, but more combinatorial, such that if we define our map D, the annulus part of D, using zeros of this section virtual omega instead of the section omega, then this D omega virtual, the new differential, will actually be conjugation of the original differential, and the second order DJs will be isomorphic. And the properties these virtual sections should satisfy, in addition to being generic so that we can count the zeros, is that at the boundary, the limit should go as follows. So for non-split boundary, it should be plus or minus infinity according to the actual obstruction section. And the signs of that are easy to see. But for split boundary, it should converge to the value of omega virtual on the annular part. And the point here is that now we can choose arbitrary values for these omega virtual on M0P and extend M1P accordingly and count zeros of those. So it becomes some sort of combinatorial count instead of count of annuli. But as I said, the DGAs are isomorphic. And the idea behind this is quite interesting. So I will give a small I will give you some idea, hopefully. So there is a new type of Reidemeister move here, which kind of is invisible in the Lagrangian projection and happens when we cross knots that contain annuli of index -1. And at these points, the values of omega at M0P can change the sign. So somehow we expect to have invariance after crossing these, and actually we can modify our knot to, in a way, change omega to have signs on M0P however we want. So that's sort of idea behind it. We expect invariance and we can actually change our knot without crossing through our Reidemeister 2 or 3 moves to get whatever we want. So then we can kind of already loosen up all this information on the knot and use these combinatorial obstruction sections. Okay, so that was all. Thank you very much for listening.
Thank you. Any questions?
And what are some geometric consequences of this? So what you can do with this invariant?
Yes, so some things, yeah, maybe I can say now, I don't know any examples where this invariant is different than Chekanov-Eliashberg DGA is isomorphic, any example of 2 knots. I believe probably there should exist some examples, but it's very difficult to hunt them down. So potentially it gives some sort of stronger way to distinguish knots. But maybe more interesting is to look at the bigger picture. So one can do this sort of thing. Of course, this is not limited to this setting of knots in R3. One can do it in higher dimensions, although maybe some transversality looks a bit more complicated. So one interesting thing here is that one can, for example, describe, there's this surgery presentation of linearized contact homology by Legendrian DGA. And here in this linearized contact homology, we augment all but one negative puncture. And if we leave more than one negative puncture, then these sorts of curves with more than one boundary component appear naturally and are necessary to get some sort of isomorphism there. So I think that that's, for example, interesting, something I'm thinking about now. So some sort of description of these contact homology and the full SFT potentially for Weinstein manifolds through this surgery presentation, through the handle decomposition. Yeah, and these higher invariants of the knots at which we glue the dimension and handles. Yeah.
Thank you.
Okay, thanks, Melissa. Maybe we'll have more questions for you in the end.